think we can get started. People are just going to come in as the class goes on. All right, so everyone see my screen and hear me and everything? Is that all good? Okay then. This week is going to be about the Cartesian plane, and yeah, so I've written down most of the main concepts in the notes that I posted on the classroom. So if you do want to follow along or just have your own copy, you can just get that off the classroom again. So the first concept I'm going to talk about is the distance formula, and well, actually first I should talk about what the plane refers to. I'm sure mostly everyone knows of like the axes where you have like a horizontal line that represents the x-axis, a vertical line represents the y-axis, and then every single point within this plane can be represented by its corresponding x-coordinate and corresponding y-coordinate. And basically everything here is just an application of like this system of how we can put these like pairs of values into a somewhat geometric form. So it's like kind of a way you can convert geometry into algebra. So yeah, that's the main like idea of why you would use this. So after that, we define a point on this plane as just an ordered pair x, y, and the first one represents the x-coordinate, or just like the value of x it corresponds to, and the same for the y-coordinate. And the distance formula for any 2 points is just x2 minus x1 squared plus y2 minus y1 squared, square root of all of that. So it's really just like the Pythagorean theorem. So if you do have 2 points, like here and here, for example, the difference in x coordinates is either going to be, it's just going to be this horizontal length right here. And then the difference in y is going to be the vertical length. And then by the Pythagorean theorem, the distance between 2 points is just going to be like the square root of their squares. So that's why that's distance formula. And since it's squared, it doesn't matter the ordering, because the square root of positive and square root of negative is still going to be positive. So it doesn't actually change the value. Right, so that's really the most basic thing to know about the Cartesian plane. So next we go to lines, and lines are basically just equations that you graph onto the plane, and they're always of the form y equals to mx plus b, or they can be changed into that form through just manipulation of the equation. And m is the slope, b is the y-intercept, and the y-intercept is just the intersection of that line with the y-axis. And basically the intersection of 2 lines is the solution of like the system of the 2 lines. So that means that the point of intersection is going to be like the pair xy that satisfies both equations. And equal slopes are parallel, and negative reciprocals are perpendicular. So like a line with slope 2 and negative 1/2, or these 2 separate lines with slopes 2 and slope negative 1/2, they would be perpendicular. And 2 lines of slope 1 would be parallel. So that's what I mean by that. And parallel just means the lines never intersect, and perpendicular means they form a 90-degree angle. And lastly, slopes that are negative to each other, so something like 2 and negative 2, are just going to be like the reflection of the line over a horizontal or vertical line. So something like a slope 1, when you reflect it over like a vertical line, it becomes a slope -1. And if you reflect over the horizontal line, it becomes the same line still, and still a negative slope. So when you reflect a line over a vertical or horizontal line, then you just take the negation of the slope. So yeah, that's really it for lines. Again, if you do have any questions about anything I talk about, you can ask. So next I'm going to talk about conics, and conics simply just refer to these curved shapes. And for the most part, you're really only going to need to know those that are like second degree equations in this level of math. And by second degree, I just mean that the highest power of the variable is going to be 2. So the most common like conics that you'll see are going to be circles and parabolas. A circle is just an equation of the form x minus a squared plus y minus b squared equals to r squared. And this is just a circle with radius r centered at a comma b. So this is really just if you see this equation or anything like similar to that, just know that on a coordinate plane, it would be a circle. And a parabola is simply just a standard quadratic equation. Y equals ax squared plus bx plus c. That's just a parabola. And a parabola is shaped just like this, kind of like a U shape. It could also be upside down. That's also a parabola. And the way you can tell if it's the right side up, like this, or like upside down, like that, is if the leading coefficient or the coefficient of the x squared term is positive or negative. If it's facing up, it's positive. If it's going down, it's negative. Right? And similar to how a line has a slope-intercept form, you know, y equals mx plus b, where you have really easy like identifying information of the line just given to you from the equation. A parabola also has something like that. This is called the vertex form of parabola. So you can do something called completing the square for the quadratic equation to like make it into something that looks like a times x minus h squared plus k. H and k are just random variables, but for a reason they're just like most commonly used variables when it comes to this form of equation. So yeah, that's why those are those variables. And simply put, this has like a vertex of h comma k. So this parabola's vertex is just h and k right here. And it's just important to note that there is a negative sign within this formula. So like if the equation is something like x plus 1 squared plus 1, and the vertex is negative 1, 1, and not 1 comma 1. And that's really it for graphing these conics. So are there any questions on that? I think most of the time with like parabolas, you don't necessarily have to know how to graph them. Well, it's just good to know, because a lot of times these parabolas are more about just like knowing the equation of a parabola so that you can find intersection points with lines or other equations. So yeah, okay. So the next type I want to talk about is absolute value equations, and the one that I listed here is an example of a rhombus, and the description is rhombus with center h comma k, diagonals of length 2a and 2b, and the diagonals are going to be perpendicular. So the reason why that this is a rhombus is because each absolute value can either be written as like x minus h or h minus x, for example, depending on like whether x is greater than h or x is less than h. And if the x and the h are like, or like when you go from one of these equations to the other, you essentially like flip the slope of the line whenever you do so, which is why you'll get a rhombus shape. So again, like it'll be like centered at h comma k, and then there will just be 4 lines around it like that. And in general, equations where you see both the x and the y in absolute value signs, and the x and the y are both degree 1 terms, you'll get some form of parallelogram. And that's because when you take the two positive values of the absolute value and like the two negative values for the absolute value, you'll get the same slope either way. So that's the way you'd get two parallel lines, two sets of parallel lines actually. So yeah, again, this is kind of like, this isn't a very common type of equation to be tested on, but it still is good to know how to handle it if you do see it. And especially if you're not like completely sure of how to deal with these absolute value equations, the best way to do it is just to use casework. And by casework, you just have like the cases to consider where x less than h, x is like greater than h. The equal to h part is not really important, since that's just going to be the intersection of these two cases essentially. And you have the y less than h case, and the y is, well, not h, the k case, like this. These are all the possible possibilities you have to consider for absolute value. And then you can just mix and match, so to speak. So there are going to be 4 total cases to consider. And then for each individual case, you just graph the line that that case gives you, and also like make sure you stay within the constraints for x and y. So for example, in the diagram, something like this, if you actually did all the absolute value cases, you get just these 4 lines extended just forever. But like the restrictions on the like x is less than h and y is less than k, these restrictions on like the lines in those cases will just cut off the parts that extend outward, and until you're left with just a closed shape, which is just a rhombus. Again, this is kind of extra. So yeah, like what I've written is really just what's important to know. All right, and lastly, I think the important part, or the most important part at least, is that these coordinates, this coordinate plane, can be used to solve geometry-like problems through a more algebraic way, and vice versa. You can also solve algebraic problems geometrically. And a lot of times, what's helpful here is that it can sometimes allow you to find lengths, slopes, and like other information that is not easy to find without coordinates. And you'll see an example of that later on. And the only really con for this type of solution is it's going to be bashy sometimes, because you have to write out lots of lines and solve quite a lot of equations in the process. So like when you do see a problem, a lot of times you have to evaluate whether you think it's worth it to like put in that time to try to solve using this method. But usually when you see lots of right angles, so if the problem has rectangles, coordinate geometry is a really good way to go usually. All right, so you'll see an example later of that. So the next one about using geometry to solve coordinate problems. Again, this is really kind of general, but you just use the coordinates to find side lengths and stuff from what you're given. So a lot of times you'll be given just lines and stuff, and they're basically just giving you a geometry problem, but you have to just do an extra step to like figure out what the actual problem is before doing it. So again, it's not really a technique. It's more just sometimes you'll see it and you'll have to know how to get the geometry problem from what you're given in the coordinates. All right. This is all really stuff we talked about. Now the graphing, and this kind of summary of what I said before and how you should go about graphing each of these shapes. And yeah, reflecting a point over a line. So when you see like a problem about reflecting, and you will see that in coordinate problems. So if you have any line and a point, and reflect like a point over the line, you would just draw a perpendicular from this point to a line. Then you would draw like another perpendicular of the same length, and then the point that you'd end up with is the reflection. And if you want to find the coordinates of that, and you knew the equation of the line, then you can find like the slope of the line that is perpendicular to the original line. And since you do know one point on that line, so you know the slope and the point on the line, you can uniquely determine that line. So from there, you can use the distance formula to find this distance, and then just like move it over again. So this isn't very common either, but it is still good to know the method for it. All right, and I do want to mention, if you are reflecting lines over lines, it's kind of the same thing. It's like you're reflecting a point over, it's like you're reflecting every single point over the other line. So yeah, that's really it for that. And lastly, just some general tips. You need to draw a decently scaled diagram. Again, with geometry problems, you want to draw just accurate diagrams. They don't have to be like super pretty, but as long as they get the job done, it's okay. Identify all useful coordinates and lengths. That's basically just, again, make sure you use all the information given in the problem, and then just solve for stuff. That's really it. And again, I've talked about these last ones already, so I won't really emphasize them too much. But yeah. So yeah, that's really it for the lecture stuff. It's kind of hard to explain like these methods just from like theory, I guess you could say. So it's really helpful just to look at problems to see it's like some hands-on kind of work. So the first one I wanted to go about was the one I mentioned earlier, which was about coordinate geometry in a rectangle. So yeah, here's the problem. So the rectangle ABC has these side lengths, so you can just draw it out. ABCD is a rectangle. Sides are 5 and 4, like so. And E is on AB, so EB is 1, so E is probably like around here. And this is 1, this is 4. G is on BC, so CG is 1. That means that G is here. And lastly, we have F is on CD, so that DF is 2. So you probably have something like this. And then FC is 3 because it's a rectangle, so that CD is also 5. All right, so now segments AG and AC are drawn like this, and EF like that. They intersected these 2 points. All right, and this would be Q, this would be P, and the question asks for the value of PQ over EF. Right. So I guess the main idea here is that if you look at the problem just right here, it's not really too simple to just like do this strictly geometrically. It's not. I think it is possible, but I don't really think it's the most understandable way to do so. What did I control V? I don't know what I did either. Okay, well, yeah, I'm just gonna like show how this one can be done using the method I described earlier. So essentially, you can kind of cast this diagram onto a coordinate plane, and the first thing you do is let one of your points be the origin, and I'm going to let A be 0, 0, since it's the easiest one to work with. It makes all the other points positive, And yeah, a lot of lines go to 0, 0 as well. So then from there, after you do that, the next thing to do is identify the coordinates of all the other points. So for example, E would be 4, 0, B would be 5, 0, G would be 5, 3, C is 5, 4, F is 2, 4, and D is going to be 0, 4. Right? So then now what you can do is using all the points you know, you can write the equation of the lines of AC, AG, and EF. Right? And once you know those lines, you can find the intersection point of all of those lines. So P and Q can be found by solving a system of equations using the line EF and the two lines AC and AG. Then once you have the coordinates, you can actually go and solve the problem. So the first thing to do here is to write the equations of the lines. And since A is the origin, it makes things really easy because the y-intercept is 0, which means that the equation is going to be y equals mx, where m is the slope. So we just need the ratio of y over x. So that just means AC is going to be y equals to 4 over 5 x. And the way you can check that these are right is just by plugging in the points. So 5, 4 satisfies this equation, and 0, 0 satisfies it too. So we know this is the right equation. Similarly, AG is going to be y equals to 3 over 5x. And yeah, so now EF is going to be another line. It's going to have slope of -2 because F minus E, the y coordinates is 4 minus 0. I'm sorry, the y coordinates is going to be 4 minus 0, and the x coordinate is going to be 2 minus 4. So 4 minus 0 is 4, 2 minus 4 is -2. So the slope is 4 over -2, which is just -2. And then now to find the y-intercept, you can plug in the points here. So if we plug in 2, 4, this is -4 and it equals to 4. So that means you have to add 8 to make it make the equation equal. So again, if you can check this by plugging in 4, 0, and it does work, which means that the equation is correct. So now we have the equations of each of the lines. So you can find the intersection points of P and Q. Right. So P is going to be the solution to the system y equals -2x plus 8 and y equals to 4/5 x. There's only one point that should work for both of these equations. So that point must be P. And if we do solve it, you can just substitute so that -2x plus 8 equals to 4/5 x. You can kind of find that 14 over 5x equals to 8. So x equals to 40 over 14, or 20 over 7. And I'll put off solving for the y coordinate of P until later, because you don't actually need to do that. So now let's solve this other set of equations, which is AG and FE, or point Q. And this would be -2x plus 8 equals to 3/5 x. And you can solve this as well. You'll get 13 over 5x equals to 8. So x equals to 40 over 13. So essentially, we know that Q has x coordinate of 40 over 13, and P has an x coordinate of 20 over 7. So now we can kind of apply this similar triangles thing, where if you draw a perpendicular from F down to this rectangle, or not rectangle, side AB, and you can draw a perpendicular down from P and across to Q. So if you form a right triangle, like with P and Q as the vertices of the hypotenuse, and the side lengths of the right triangle being parallel to the sides of the rectangle. And again, this is kind of possible because we're given it's a rectangle. You know that like this small triangle with PQ as the hypotenuse must be similar to this bigger triangle with FE as the hypotenuse and just another random point. We can call it like h as the base of the altitude from f. This like FEH is similar to this triangle with P, Q, and this other point here. And what's special about this is that we know that this bottom length, the horizontal length of this, the horizontal leg of the right triangle with P and Q on it, is that length is going to be equal to the difference in x coordinates between Q and P. And this is really just by the definition of our coordinate system. That's how we could find this length. And we know the length of E to H is just going to be 2 because it's just like 4 minus 2. AE is 4, and AH is going to be equal to DF, which is equal to 2. So the difference is 2. And like this horizontal length right here over EH is going to be equal to PQ over EF because they're similar triangles. So what that means is that our answer is just going to be 40 over 13 minus 20 over 7 all over 2. So yeah, that is the answer. And this actually simplifies down to 10 over 91. So yeah, that's it. 10 over 91 is the answer. So are there any questions on this? Kind of just wanted to go through it just as an example of how you would use coordinate geometry in equation in like a problem that doesn't explicitly tell you that you can use coordinates for. Oh, and if you are curious, so how are these two triangles similar? Well, I'll just take this triangle FEH first, okay? So, you know, FEH, it's just this right triangle that I pulled directly from the diagram, and P and Q are just points on F and E, right? So I can just draw out a line from Q that's parallel to EH. And this is just an arbitrary line, so there's really nothing wrong with drawing that. And again, I can draw one for P that's parallel to FH. And basically, these two lines are perpendicular because they're each parallel to the sides of this right triangle, and since the sides of the right triangle are going to be perpendicular, these two lines must be perpendicular as well. And then from there, since we have two parallel lines and a transversal, basically, these angles are going to be the same. So we know that this like angle right here next to the Q is going to be equal to this angle at the E. And since we have these equal angles, where all the angles of like this right triangle and the big right triangle are equal, that means they're similar. And the property of similar triangles is that like the corresponding sides, the ratio between them is going to be the same. So the ratio of this side to this side is equal to PQ over EF, and it's also equal to this height over FH. So that's how you would use the similar triangles argument. And again, if you don't see that, you could actually just find the y coordinates of P and Q and use a distance formula. It takes longer, but it should work as well. So does that answer your question? All right. And if you are curious on how you could do this problem without using coordinate geometry, I think the way that you would do this is by extending AG past the line until it intersects with CD again. So like if you extend both of the sides to another intersection point, then you would have like these two sets of similar triangles with AEP and FPC. And I can just show them right here. You'd have like these two triangles are similar, and these two triangles. The green's not showing up very well. Like you would have these two sets of similar triangles, and then you could use the ratio of their heights. And since you know the fixed height is 4 here, then you can find the heights of basically each of these triangles. So once you know the height of the red triangle, the height of the green triangle, you can just subtract them to find the height of PQ. And then after that, you could just find like the ratio between PQ and FH. So I think that would be how you would do this problem without using coordinates. So again, I just want to show that these problems are like pretty straightforward without having to use this kind of method, because with the symmetron method, it might be hard to, for one, think about extending this line past the diagram, and you have to keep track of ratios and stuff. Whereas these coordinates, they're very reliable because it's really easy to check your work with coordinates, as you have to like plug everything into equations anyway. So it's kind of harder to mess up. So yeah, that's all I wanted to say with this problem. So, all right. So that out of the way, I think that was really the only one that I considered to be kind of mandatory to go over. So I guess from there, I can just start from the front. So this problem, top left, that points A equals 0, 0, 0, B equals 1, 0, 0, C equals 0, 2, 0, and D equals 0, 0, 3. Points E and F and G and H are midpoints of these line segments. What is the area of EFGH? So the reason why I chose this problem is because it's only one of 3D coordinates. I just wanted to like demonstrate that how you can deal with coordinates 3 dimensions and how they're really not all that different from 2 dimensions. So the only hard part is really just drawing out your diagram, because again, it's you can't really draw 3 dimensions in 2 dimensions. So anyway, I like to draw it like this, where we have X, Y, and Z coordinates like so, and it's kind of inverted, but I consider like all these lines as the positive axes respectively. So we know A is just going to be the origin. B is 1, 0, 0, 0. So that means it's going to be on the x-axis at length 1. So I'll just put that here. C is 0, 2, 0, means it's on the y-axis and distance 2 away. And D is 0, 0, 3. So that's going to be a distance 3 away, while on the z-axis, like that. So it's like 1, 2, 3, and B, C, and D are like that. All right. So now EFGH are midpoints of BD, AB, AC, and DC. All right, so we can kind of draw this out. DC, BD. So I think it's pretty clear this is like a tetrahedron. And BD, midpoint's like right here. AB's midpoint's here. AC's midpoint is here, and CD's midpoint is, here's a different color. Our 4 points are here. EFGH. It doesn't really matter like where I labeled them, just know those are the 4 points. Right, and what's the area of EFGH? So the main thing with this problem is that you have to find the coordinates of each of these points. So you can kind of use this midpoint formula basically. And I didn't actually go over this, but in coordinates, to find the midpoint of 2 points, you just take the average of each of the coordinates of those 2 points. It's kind of, you can think of it as kind of, you can think of it as like kind of intuitive. The midpoint is just like the middle of everything, so it's kind of like the average. So if we take BD, for example, 1, 0, 0, 0, 0, 3, this midpoint is going to be 1/2, 0, 3/2. And it's because average of the x coordinates is 1 and 0, this is 1/2, Average of the y coordinates is 0. Average of the z coordinates is 3/2. Right? And so for AB, this is going to be 1/2, 0, 0. For AC, it's going to be 0, 1, 0. And for CD, it's going to be 0, 1, 3/2. So now the cool part here is that now that we know the coordinates, we can actually show that this is a rectangle. And all you really need to show for the rectangle is that these lines are going to be parallel and they're going to be perpendicular, or like two sets of parallel lines and the intersecting lines are perpendicular. So to show that they're perpendicular, I guess you have to use kind of the fact that if we have two perpendicular planes, any two lines like that intersect on the intersection of the planes are going to be perpendicular. So it's like, think of like how the XY plane is perpendicular to the XZ plane. So any line that is on this XZ plane is also perpendicular to the line on the XY plane. So that's why this would be like a 90-degree right angle. Yeah, that's kind of the only explanation for it. And yeah, so once you like know that, you can just find the side lengths to find the area. So yeah, the lengths here are going to be, if we mark this out, this is going to be 3/2, I want to say. And this one is going to be, we can use a distance formula for this actually. So this point is 0, comma, not comma, it's going to be 1/2, comma, 0, comma, 0. And this point is going to be 0, comma, 1, comma, 0. So the distance is going to be a square root of 1/2 squared plus 1 squared. Or the square root of 1 plus 1/4, or √5/2. So then like the area is just going to be the product of that, which is going to be 3√5/4. So yeah, that was kind of messy, but again, the concept is just you can use coordinates to find like the relative locations of the points to each other. Then from there, you can determine a shape, and then once you know the shape, find the side lengths, and then you find the area. So yeah. All right, so let's move on to this one. So a triangle with these vertices is reflected above the line, about the line, x equals 8. To create a second triangle, what is the area of the union of the two triangles? So this directly ties into what I said about reflecting over a line. So first you can just graph the points. 8, -3 is around here, 9, 1 is like here, and 6, 5 is probably somewhere around here. And this line x equals 8 goes directly above, or not above, but like through this point. And so when we're like reflecting a triangle over a vertical line, instead of just reflecting like the area, you can reflect the vertices and whatever happens. So like if you reflect the vertices of the lines like this, and it would connect the three vertices, you'll have that same triangle, except for just flipped over a line. So if you like flip the vertices and connect them, you'll still end up with the reflected triangle. All right. So that's kind of what your diagram is going to look like. And I guess the cool niche part about this problem is that the reflected vertex 9, 1, when you reflect it over to the other side, it's actually going to be on the line between the other two vertices. I guess this is kind of just part of the, this is kind of just how like the problem writers decided to make the problem. I think you can verify this just by checking the slopes. And yeah, so like this 9-1 basically goes to 7-1, this point, and the point's like 6-5 and 8-3. It's kind of unresponsive this time. They're all going to be like on the same line because this line has a slope of 4, and if you check any 2 points, you'll get a slope of 4. So slope of -4, sorry, you'll get that. They're collinear. So that's why I drew the diagram like it is. So now the problem is to find the area of the union of these triangles. And so from what we know here, we can just change this to now just a normal geometry problem. The union refers to just all points contained within either triangle. So you basically count the overlap section just once. So basically we just ask the area of something of a shape that looks like this, and it has like an axis of symmetry here. All right, so there are multiple ways to do this. I guess the easiest way would just be to use base times height. And the base would be this line in the middle, and the height would just be 1. Not 1, it would be 4. Actually, no, never mind. I should stop doing things in my head. This line, this height here is going to be the same distance from this x-coordinate of the point 6-5 to the vertical line. So the height should be 2 on either side. And the base is just going to be the distance from 8-3 to this intersection point on the line. So yeah, that's really all we need to find, this intersection point. So the points are going to be 6-5 and 9-1. And this intersection point with line x equals to 8 is going to be the this point right here. So again, from here we can just write the slope of the line is -4/3. And when you plug this in, you can find that the equation of the line is going to be y equals to -4/3 x plus 13, I believe. Yeah, okay. And then from here, just plug in x equals to 8. And this gives y equals to -32/3 plus 13, or 7/3. And this is because 13 is 39/3, so 39 minus 32 is 7/3. That means that this length is going to be equal to the difference in y coordinates because the x coordinates are the same. So the length that we need, or this like base that we're using, is going to be 7/3 minus -3, which is 16/3. So that means the area of the entire thing is just going to be base times height, and the height is 2, and the base is 16/3. So the area is just going to be 32/3. And note that I didn't divide anything by 2, and this is because this 2 times 16/3 just represents twice of the area of one of these triangles. Since we're calculating the area of 2 of the triangles, we don't have to multiply, we don't have to divide anything by 2 because you're going to be multiplying by 2 right after to find the area of 2 of those triangles. So it's simply just 2 times 16/3, which equals 32/3, and that's the answer. So are there any questions on how to do this problem? Again, you can just think of it as like a different style of geometry where you still have to identify like what you need to figure out. to solve the problem, but like to actually get the information that you need, you'd have to use coordinates to find it. All right. Everyone good with that? Okay, so let's go to the next problem. 2013 10A number 18. The points A equals 0, 0, B equals 1, 2, and C equals 3, 3, and D equals 4, 0. So off the bat, I can just draw the first quadrant since everything is going to be a positive coordinate. A 0, 0, B is like 1, 2, so maybe around here. C is going to be 3, 3, and D is going to be 4, 0. So A, B, C, D looks something like this. Right? Quadrilateral ABCD is cut into equal area pieces by a line through A. That means it's going to be some line, it'll probably be like this or so, that cuts this into equal areas. And the idea is to find the intersection between this line and CD, so this point right here. So when you see this kind of problem, you kind of have to make a list or some kind of strategy to solve the problem. All right, so if you do know how to do it, yeah, you can explain it. Yep, that is one way. That's called, or not really calling anything, but I think of it as like a piecewise way to find area, where you make a rectangle and then subtract off triangles. Your second part is a bit shaky. You can't divide by CD, but or I guess you probably, I think I know what you're saying, but basically the idea is first find the area. That should be your first step because since we know equal areas, we need to find the area to be able to work with that. Then after that, you take half the area and find this y coordinate of the point. I'll call it E. You can find the y coordinate of E. And because we know like what half the area of this shape should be, and we know this base, then we can find the height. It's kind of just like reverse finding the area. You already know the area and you already know the base, so you can find the height. And the height is the y coordinate of E because of like how we're in a coordinate plane. So, and then from there, once you know the y coordinate of E, you can find the x coordinate of E from the line, from the equation of the line CD. So this is because CD is like made up of 2 points, so you can, and you know the 2 points, you can find the slope between the 2 points, and you can find the y-intercept. So you already know the line CD, and then from there, we know E's y coordinate. So like if you plug in the value of y into the equation for CD, you're only going to get one value of x that works. So that value of x has to be the x coordinate of E. So that's how you could find the x coordinate from just that information. And then from there, well, that's kind of the problem. That's all you have to do. You just have to find the point and that works. And yeah. So yes, that would be like the steps to the problem. So again, we don't have like, I don't think we have too much time left. So I can't really kind of solve or like crunch numbers basically for this entire problem. But like this method should be enough to solve the problem by yourself if you do so after class. And so yeah, this would be how you would do the problem. And main takeaways would just be like how you should approach the problem more so than, again, just what like the answer to the problem is. All right, so if that is good, I think we'll go on to the next one. So this one says a line that passes through the origin intersects both the line x equals 1 and a line y equals to 1 plus square root 3 over 3x. And the three lines intersect to create an equilateral triangle. What's the perimeter of the triangle? So I think with this problem, what you really kind of need to figure out is, I guess, what equations of equilateral of lines that are part of equilateral triangles would look like. So I think first off, I'll just draw the lines that we do know. X equals to 1. I'll make it kind of bigger. So let's say 1 is here. And we know the y coordinate of the other line is also around 1. Square root 3 over 3 over 3. Square root of 3 over 3 is going to be less than 1. So I'll draw the slope kind of like flat-ish, like this. And we know that this is really messy. I'll extend like that. And we know that another line passing the origin, so something like this, intersects to make this equilateral triangle. And really the really like important takeaway, or not takeaway, observation here is that the slope square root 3 over 3 is not just an arbitrary slope. So if we do consider a line that has slope of square root 3 over 3, this is kind of the same if we divide everything by square root of 3 as a slope of 1 over the square root of 3. And if you use the Pythagorean theorem here, you'll see that this is 2. And what's important about this is that this is actually just a 30-degree angle, or half of an equilateral triangle. If x equals 1 has slope nothing, yes. So we'll get there. And so the important observation is that this is half of an equilateral triangle, and also this x equals to 1 line has slope of undefined, or the vertical. This must mean that the triangle is symmetric, like about a horizontal line. So like if we do reflect this line over an axis, you'll get an equilateral triangle like so. So from like reflecting like a line over an axis, you know, that just has a slope negative of what it originally was. And the original slope is square root 3 over 3, and it passes through 0, 0, meaning the y-intercept is 0. That means that this slope is, or this line is just y is negative root 3 over 3x. And now all you need to do is find the perimeter of the triangle. And to do that, all you need is a side length. And the easiest way to find a side length is just to find the coordinates of these 2 points here and subtract them. And this is just like the solution over the intersection of x equals to 1 and these two equations. So like with the top one, it's just going to be like 1 comma 1 plus root 3 over 3. And then the second one is just going to be 1 negative root 3 over 3. This is from plugging in x equals to 1 to the equations. And then when you subtract the y coordinates, so 1 plus root 3 over 3 minus negative root 3 over 3, this is equal to 1 plus 2 root 3 over 3. Since this is one side length, you have to multiply by 3. So the perimeter of the entire thing is just 3 plus 2 root 3. So I guess with this problem, I just wanted to, I guess, to show that for one, if you see a slope with root 3 over 3 or 1 over root 3, you should, or a slope of square root 3, you should really associate it with something that's similar to an equilateral triangle. And also from after that, try to like choose the most efficient like points to use. So like it's a lot easier to find distance between these 2 points than like any of the other 2 pairs because they're not on the same vertical or horizontal line. Like in general, it's much easier to find the distance between points if the x coordinates or the y coordinates are the same, since you don't have to square anything. So yeah, that's that problem. All right, so we can move on. All right, so the next problem is how many integers x is a point x negative x inside or on the circle radius 10 centered at 5, 5. So there are a couple ways to do this. The way I want to show is the way you can convert this seemingly geometric problem into algebra. So, and this uses the equation of a circle. We know that a circle of radius 10 centered at 5, 5 has equation x minus 5 squared plus y minus 5 squared is equal to 100. And this is simply just from the formula that is on this note sheet. So yeah, this is like the equation of a circle. We know that x negative x, this point is inside or on the circle. So like I kind of want to consider what happens if we plug in x negative x into this equation. And I guess you can do this because this will create an inequality. So which I'll address later on. So if we do plug in x negative x into the equation, this kind of gives like any boundary points, so to speak. So x minus 5 squared plus negative x minus 5 squared equals to 100. And then you can simplify this. So x squared minus 10x plus 25 plus x squared plus 10x plus 25 equals to 100. So like 2x squared plus 50 equals 100. 2x squared equals to 50, or x squared is equal to 25. This means that the boundary points are going to be where x equals to plus or minus 5, right? That means that if x negative x is like going to be on the circle, it's going to be at the points 5 and negative 5. So now if you think about it, the circle, like since it's like centered at 5, 5, which is going to be like within, never mind. So actually, I think we'll put it this way. Once we know that 5, negative 5 is going to be like the boundary points, then that must mean that x is going to be less than or equal to 5 and greater than or equal to negative 5. And I guess I'll actually just draw it. So if we know 5, 5 is this point and the radius is 10, let's see, it's gonna be like, circle is gonna be something like this. Right. So like the points with like 5, negative 5 and negative 5, 5, they're gonna be like these kind of quadrant outer points right here. And then any point x negative x that is like inside the circle has to be like on this line y equals negative x. So all of these like points that I've like kind of dotted in red are going to be x negative x and inside the circle. And as you can see from the diagram, anything outside of negative 5 is going to land outside the circle. Anything inside is going to be within the circle, which means that any value of x between negative 5 and 5 will work. So this is just a total of 11 integers, and that's just the answer. So yes, does everyone kind of follow? This is just, I guess you could say this is like an algebraic way to confirm something that you can see in the geometric graph. So we have like 1 more minute, so I'm going to be skipping this problem. It's really not that hard. So yeah, if you're interested, you can go like look into it. I want to get to this last problem because it's about absolute values. So this says area of the region is x squared plus y squared equals absolute value x plus absolute value y. Find the area of the region. This means you have to graph it and see what shape it's going to be. And I guess the key concept here is that this equation thing is going to be symmetric. about like x is positive or x is going to be symmetric in all 4 quadrants. So what I mean is that x squared and y squared are not going to be affected by whether x and y are positive or not, and neither is absolute value of x and absolute value of y. So like if we graph the equation in just one quadrant, like x is in the first quadrant, for example, where x is greater than 0 and y is greater than 0, it's going to have the same shape in all 4 quadrants, and you can just reflect it over. And also, since the coefficients of x and y are the same for x and y, we know that it's symmetric over like the equation y equals x as well. So you don't actually have to worry about like whether flipping over the x or y axis, because it should give you the same result. But either way, I think it's first better to show like how we would actually find this shape. So if we assume that this is going to be in the first quadrant with x is greater than or equal 0, y is greater than or equal 0, we can take away the absolute values. And since x and y are greater than 0 in this case, their absolute values are just x and y. Then from here, move everything to one side. And now you can do something called completing the square, which basically, if we add 1/2 to each side, we can change this into x minus 1/2 squared plus y minus 1/2 squared equals to 1/2. So what I did is just like added 1/4 to each of like these x squared minus x, y squared minus y, and then we can change them into this. And this is because the expansion is going to be x squared minus x plus 1/4. This expansion is going to be y squared minus y plus 1/4, and like the 1/4, 1/4, 1/2 cancel out to 0. So that's why these equations are equal. And this is actually a very, very common way to convert something that isn't like immediately in the equation of a circle into a circle. And what's great about that is that it gives us a definite shape we can graph. So this has a center of 1/2, 1/2, which is like right here, and a radius of square root 2 over 2. Because remember, this constant is going to be the square of the radius. So then from there, we can just draw a circle. It just so happens that square root 2 over 2 is the distance from this point to the origin. So you know it's going to be like a circle that passes through the origin like this. Right? However, you have to keep in mind the restrictions on x and y. We know x is greater than y, sorry, x is greater than 0, y is greater than 0. That must mean that any like part that's outside of the coordinate, like first quadrant, is not going to be a part of our diagram. So we have to like get rid of this part that hangs over basically until we're left with this kind of weird shape in our quadrant. And then you kind of just have like 4 of those in all your other quadrants as well. So it would look something like this as the shape of the graph of the region. And now to find the area, you could just find the area of one section and multiply by 4 or anything. So basically, from there we can draw a line from these points and it goes through the center, and you're going to be left with an isosceles right triangle and a semicircle. So if you do want to like verify that this is true, you can simply just plug in x equals 0 and y equals 0 into the original equation for the circle to find the coordinates of these points here. And then you can verify that 1/2, 1/2 is on the line between the 2 points. And I'm not going to do that here for the sake of time, but if you do want to like verify that, as that's technically the more rigorous thing to do, go for it. But what that does is allows us to calculate the area of a semicircle and a triangle. And these are all things that are very manageable. So yeah, basically this is 1/2, 1/2, and this is like the midpoint of the hypotenuse, which means that the side lengths of this triangle are going to be 1. So if we draw a diagram again, it looks like 1, 1, and then the radius is going to be root 2 over 2. So the area is going to be 1/2 plus root 2 over 2 squared times pi divided by 2, which is pi over 4. So then there are 4 of these, so you multiply everything by 4 and get 2 plus pi as the answer. So yeah, are there any questions? All right, well, if not, class is over. You guys can leave. Again, everything is posted on the classroom if you need it. So yeah, kind of the same drill as the past few weeks.
Thank you. Bye.
Bye. Take care. Good.